Hello, good morning. This is mechanical vibration, the continuation of mechanical vibration lecture. It is about vibration under a general forcing condition. So this is lecture 9. So the objective of learning this part is just after completing this topic, you should be able to find the response of system, a single degree of freedom system, subject to general forcing using Fourier series. Use the method of convolution integral to solve systems subject to arbitrary force. Find the response of system subject to earthquake using response spectra. Solve the system subject to impulse, step, and ramp force using Laplace transform. Under the characteristic of and understand the characteristic of transient response, such as peak time, overshoot, settling time, rise time, and delay time, and procedures for the estimation. And finally, apply numerical methods to solve vibration problems. There are different numerical methods to solve the vibration problem. So these are the learning objective of this topic. So introduction, as we know in our previous lecture, we consider the response of single degree of freedom system subject to harmonic excitation. That means maybe we consider cosine functions or sine functions. The response is considered as a harmonic, either harmonic or it is exponential type of solutions are considered before. Or even the forcing function considered in the previous lecture are such simple forcing case. But in the real world, many systems are subject to several types of forces, that forcing functions that are different from harmonic. So we consider those types in this lecture. The general forcing functions may be periodic, or but non-harmonic, or non-periodic type. So non-periodic forces include the force such as suddenly applied constant force. We call that step force. Means, for example, a drop of ball on a structure surface considered as sudden impulsive force. So that is different from the force which we expect continuous sinusoidal force. A linearly increasing force like ramp force and exponentially varying forces. Okay, so the forcing function or excitation of short duration compared to natural time period of the system is called a shock or impulsive force. Here we have some examples of the type of forces which we encounter when we consider this general forcing condition. The motion of cam by to the follower. So most mechanical students are familiar with this system. This is cam follower system. So this is the cam, and this is the follower. No, this is the roller, and there is a follower, which this is a power transmission or motion transmission case. We have such an arrangement. So there is a contact between the roller and the cam. So the cam is pivoted about this point, and it is rotating about this point. So there is an eccentric kind of, or the shape is not regular in the cam case. So because of that, motion transfer will take place. And the load applied at this point, the normal component, the tangential component of loads are there. So many things are there. Okay, so this is the cam follower mechanisms. So an abrupt change of loading on the due to the profile difference, we can see various type of forcing function here. Again, we see here the hydraulic forging machine. That is, the forging machine will used in the metal forming or processing. So that forging machine provides an impulsive force to the structure. Again, the force applied, the motion of automobile when it's moving in the road is uneven profile, like old roads, which are having a lot of photo holes. So you see there are a lot of photo holes. So the car will subject with different type of forces, and the ground vibration of the building frame during an earthquake means when the earthquake happens, the ground transmits motion to the building that can be uneven type of, so which is not expectable kind of load. So that is another example of this case. If the forcing function is periodic but not harmonic, it can be replaced by sum of harmonic functions using harmonic analysis procedure discussed as the previous section. So what it is, if we consider the harmonic type of analysis, means our forcing function consider periodic but not harmonic, then we can make a superposing of the forcing functions. Just using the Fourier series, we can use the constant term with the constant. We can use the harmonic part of the solution with the harmonic. So by doing that, we can find solution for the this case. So using the principle of superposition, the response of system can be determined. Okay, so the superposing the response due to individual harmonic functions that we can I will show you with example in the coming in this lecture also. So the response of system subject to non-periodic forces commonly obtained using various methods of analysis. One of the method of analysis is convolution integral method. Another one is Laplace transform method, and the third one is numerical method. So what are these three? We can see them one by one. So maybe for the first time, we can see Laplace transform method. And in the next lecture, in the another day, we can see convolution integral, and finally, how we can use numerical method. So that is the content of the lecture. So let's come to the Laplace transform case, because this is the part that we are going to Laplace transform, and the Fourier series are the one which we are going to apply in the preceding lecture. So at the very beginning of our vibration lecture, in the introductory, I tried to cover some mathematical aspects like the partial differential, how to solve partial differential equations, how to solve the Laplace transform, and various trigonometric relations which are helpful in the analysis of vibration. So we have seen those things, but just to revise again, Laplace transform is one of the mathematical approach that we can use here. So that actually this is a simple definition of what the Laplace transform and who invented it. Okay, so it is the inventor of Laplace transform is the Fourier Simon Laplace. Laplace is an integral transform that converts the function of real variable to the function of complex variable. Okay, so in the complex frequency domain. Computation of Laplace transform of functions derivative. So let's what it is. It is convenient to use a differentiation property of the Laplace transform to find the transform of functions derivative. This can be derived from the basic expression of Laplace transform as f of s, the Laplace for a function f of t The Laplace transform of this function f of t is, we represent it with f of s, which is equal to the Laplace transform of f of t. This f of t is the forcing function in our case. In our vibration analysis, this f of t is the forcing function, which is equal to an integral of 0 to infinity e raised to minus st f of t dt. So this is the method, the formula that we can. So differential equations, Laplace transform. How we can do the solution for this this differential equation? The first thing is, differential equations is given. It is, and then Laplace transform will be carried out, that using the Laplace transform, and then algebraic equations. So we have actually two paths. We can go from differential equations to algebraic equation, and from algebraic equations to differential equations. Okay, so for ordinary differential equation given, we perform Laplace transform, then finally we get algebraic equation. And for the algebraic solutions, we perform the inverse Laplace transform, and then go back to solutions to ordinary differential equations. So this is the path from here to here and from here to here. So the idea is that using L and L inverse allows for easier solution. So allows us to tackle the discontinuous functions. So the definition of the Laplace transform function L, f of s is the L transform of f of t for t greater than 0. So this is the restriction here. So this is the first equation which we have seen there. F of s is equal to the Laplace transform of f of t, which is equal to an integral of 0 to infinity e raised to minus st f of t dt. So this means what? When we integrate it in terms of f of t, we have finally get this type of equations. Means performing some mathematical approach, finally what we can get, the s times Laplace transform of f of t is equals to f of 0 plus Laplace transform of f prime of t. This f prime of t means the first derivative of the function f of t. Okay, so which finally gives us the Laplace transform of f of n. This n means the n derivative, the order of derivative means, for example, second the differential means second derivative, third derivative, fourth derivative. N can be any number of derivatives. So finally, what we can get, just observing this equation for the n is equals to 1, means here for f it is n is 1. So that Sn times Laplace transform of f of t minus Sn minus 1 s raised to n minus 1 times f of 0 minus, finally we can get the list. Okay, s naught means that is 1. S naught means 1, and we can remove this s raised to 0 because it is 1. Then f raised to n minus 1 means the last derivative times 0 of the 0. So where fn denotes the nth derivative of f. Okay, so this is the method. So integration in t leaves a function of s. That means integral of 0 to infinity dt, improper integral. But must make sure that the limit exists for this. The thing which we must understand is whether the limit exists or not. So that means for integral of 0 to infinity, integral of g of t dt from 0 to infinity, which is equal to limit of as b approaches to infinity for the integral of gt dt. If the limit exists, then convergence. Otherwise, the solution is divergence. So as example, let's take this, the Laplace transform of e raised to at. Let's take this. Use differential definitions to solve this equation. So solution. So our f of t is equals to e raised to at and integrate it. So f of s means the Laplace transform of f of t is 1 over s minus a for s greater than a. Okay. So how it is done? Let's see. Given f of t, then the Laplace transform is done. That means f of s. There is an inverse Laplace transform. Okay, that is L inverse represents inverse Laplace transform. So f of t from f of s to f of t, it is using L. But we can use instead of this L inverse from f of s to ft. So that can be shown here. The Laplace transform of f of t is equals to f of t L f of s, which implies EAT, the Laplace transform, then 1 over s minus a for this one. The inverse Laplace transform of the Laplace transform of f of t is equal to fs, the inverse Laplace transform gives f of t, which is equals to 1 over s minus a, means which implies L inverse means inverse Laplace transform of f of t, which is EAT. So we come back to the original function. So in our case, we can represent this, the Laplace transform of this is solution for this question actually. How this answer came, we can see here. So f of t is equal to EAT, e raised to at. Therefore, we substitute in the place of f of t EAT. Okay, so here EAT, e raised to at. So by definition, it has e raised to minus st is there. Again, this is f of t function. So what you can get? Minus, so minus come out, e raised to minus of s minus a t dt. Okay. So which gives us integral of this thing, which gives e raised to minus s, e raised to minus under bracket s minus a t over, because the integral of this, as we know, that direct definition of integral, we have this thing comes down here, minus s minus a, for the range of 0 to infinity. So if we substitute 0 instead of t, we can get 1 here, minus 1, because there is yeah. Yeah, first, let's evaluate it for infinity. For infinity, e raised to s minus a t. T infinity means this is a huge, very small infinity here. I'm sorry for that. There is some confusion here. Yeah, we can see here. It means D is not there. This D is not there. Sorry. Okay, so I made mistake here also. That's why confusion come. So this part first, e raised to minus s minus a infinity over minus of s minus a minus again e raised to s minus a t. T is 0 now, so the infinity part will be 0, and the 0 1 gives 1 over. Again, there is minus because of the 0 to infinity thing. So the minus minus cancel this minus. We have left 1 over s minus a, because e raised to 0 is 1. Again, another second example, similar example like this. And instead of a, we substitute minus 2. So what will happen? F of s is equals to integral of 0 to infinity e raised to st minus e raised to minus 2t dt, which is equals to e raised to minus s plus 2t dt. Similar way, e raised to minus s plus at over minus of s plus a. This is the for 0 to infinity. This d is not available, only this dt by itself not available. Let me clear this thing. Okay. This thing. This dt is not available here. That is considered as point of confusion. So now it is clear. So if we substitute infinity here, e raised to infinity, this number become this over this becomes 0, and when it is 0, we have this part 1, so 1 over this minus will be cancelled by another minus. I mean e raised to s plus 2, instead of t, we substitute infinity here, minus of this quantity, s plus 2, minus e raised to, okay, s plus 2 times t is 0 now, over minus s plus 2. So that means what? This part is 0 because e raised to minus s plus 2 infinity means this is with minus sign. You see, here it is with minus sign. That means 1 over, and instead of this, we can represent it 1 over. So when 1 over e raised to s plus 2 infinity means it is very large number. Okay, it is very large number. 1 divided by very large number means finally it becomes 0. And this part is e raised to s plus 2 times 0 means e, this is 1. So which gives us 0 minus will give us plus. So 1 over s plus 2. Yeah, that's why, which is equals to this thing. Here also the same. Here also the same. This means what? E raised to minus s minus a infinity times infinity over minus s plus s minus a minus minus s minus e times 0 over minus s minus a. So this part is still e raised to s minus a means 1 over e raised to s minus a times infinity, means that is very large number. 1 over infinity means that is almost 0. So because of that, this part gets 0, and we have left this part. That means e raised to this thing is 0. That means 1 over minus minus cancelled, so s minus a. This is the meaning of this. Okay. Example 3, let f of t is equals to t. So let's find the Laplace transform of this thing. So we directly substitute instead of f of t this t, then yeah, substitute f of t instead of f of t, substitute t here. Then what? The Laplace transform of f of t is equals to t times e raised to s minus st over minus s from 0 to infinity. So the first part 0, the next part is with, yeah. So finally, what we have left is 1 over s is there from the first part. Yeah, the whole this part is get 0. Yeah, this part is 0. From this part minus minus. Actually, what we did here is we use integration by parting. Here also integration by part also done. Okay, this is integration part. According to the rule of integration by part, u dv is equals to u dv is equal to uv minus v du for the interval of a to b. A to b. Here also we can use a to b. Okay, so in our case, we let u is equals to t in this case, and du dt is equals to 1. Why? Because t, okay, du dt 1. So that implies du is equals to dt. And the dv is equals to e minus st. E minus raised to st dt is dv. So v is equals to e minus e raised to st dt, which is equal to e raised to minus st over minus s. So substituting this thing in this relation, what we can get is this. So finally, what we can get, that is 1 over s squared. Okay, this is the relation. Actually, here also, the first part will get 0 and the next part only remains. Okay, so this is the Laplace transform of f of t. Now we have various functions. So let's see what impulsive function is. The Laplace transform of impulsive function delta t is given by this relation. Okay, so this is an impulsive function. We have various types of impulsive functions. For example, this is a representation for impulsive function. This is another ideal impulse at t0. This is ideal impulse at minus to plus some time period, minus half of the period to plus half of the period. When we transfer it to 0, it seems like this. Okay. Again here, we can see some time shifting of the. So this is a delayed ideal impulsive at t is equal to 0. Okay. Again, this is also. So how we can represent this function u of t is equal to delta t, which is equal to infinity for t is equals to 0. At t is equal to 0, it is infinity, and 0 for t is equal t different from 0. It is 0 everywhere, but only infinity at the t0. Hey, Alisha. Betul. Ah. So the Laplace transform of u of t is 1 in this case, because we consider this Dirac delta function here. And there is step functions. At t is equals to at t naught, it goes to some peak a, and then it is constant. So the function is defined as f of t is equal to 0 for 0 to t naught, and a for t naught to t. Okay, so it will go. So this is the definition that is called time shifting of state. So f of t is equal to f of t minus t naught. Then we can rewrite, we can find f of s. So f of s is equal to the Laplace transform of f of t. So from t is equal to 0 to infinity, e raised to st f of t, which is e raised to st f of t minus t naught dt. So here, this gives us 0 to t naught for f of s is equals to the Laplace transform f of s is equals to 0 to t naught e raised to st f of t dt, because we use two regions. The first region from here to here, and the next from here to anytime t. So for the first region, it is 0, because plus then for the next region, it is a est dt. A is constant here. That means this a, okay. F of t for the first region is 0, so it is completely 0 here. Okay. Finally, what we can get from this relation is a over s e raised to minus s t naught. This is the Laplace transform of this type of function. Unit step function. Here we can see the function from at 0 time, it goes to some a and then goes constant like this. So we can define this function as u of t is equals to 1 for t greater than or equal to 0, and 0 for t less than or equal to 0. Means for this portion, nothing is there. It is 0 for t less than 0, and 1 for t greater than or equal to 0. So we define this u of t. The function u of t is our f of t. So the Laplace transform of u of t is equals to that u of t times e raised to st dt. So u of t is 1 for the region from 0 to positive infinity, so that we have 1 over S. This is the Laplace transform of this type of function. Okay, so there is also ramp functions. Okay, this is the type of those functions. When integrating unit step function, we can obtain ramp function. So we can see that relation. So R of t and t is here. So this is the ramp function. Okay. So when we define this R of t, which is 0 for t less than or equal to 0, it is 0 for this side, and it is t for t greater than 0. So this is t. Okay. With some what do you call this? Slope. Okay, with some slope. So how we can define this? Let f of t, the Laplace transform of f of t is equals to L times Laplace transform t times u of t. So that is t e raised to st. So f of t is t. Then finally we can get 1 over s square using proper definition of integral and the Laplace transform function. So there are some relation from L of delta of t, L of u of t, L of r of t. The relations, that means we have such graphs which you have seen here. Okay, from here that means what? Sorry, it is stacking of the computer. Okay, it's having some problem. So impulse function, the first impulse function, the next step function, and then ramp function. Okay, this is impulse, function, then step function, and there is ramp function here. Ramp function. So we can go from impulse to step function and step to ramp function. So integrating the impulse function, we can get the step function, and integrating the step function, we can get ramp function. And also we can go back to ramp function to step and step to impulse using differentiation. Okay, by differentiating the unit ramp function, we can get unit step function, and differentiating the unit step function to get unit impulse function. So this is the relation between the three. And this is a simple summary of Laplace transform of various functions. Okay, so this is unit step function, unit impulse function, unit step function. And we have here ramp functions. So we can see their name here. And what is the, for the f of t, what is the Laplace transform? That is what we have. For example, f of t is equals to constant 1, then f of s, the Laplace transform 1 over s for s greater than 0. For f of t is equals to e raised to at, f of s is equal to 1 over s minus a for s greater than a. F of t is equal to t raised to n, then f of s is equal to n factorial over s raised to n plus 1. for s greater than f of t sine at, then the Laplace transform is f of s is equal to a over s square plus. So these are some definitions already defined functions. So one can easily refer this thing for whatever the solution become. So one can refer this table. So we have some problems related with this. So problems to be solved in this topic. Look, a linear single degree of freedom system of mass m, stiffness k, and viscous damping c is originally at rest and vibrate under linear or ramp loading as shown in figure A. Find the forced vibration, the forced vibration of the mass subjected to ramp load R of t, as shown in figure B. Okay, using Down's integration, the method of undetermined coefficient, zero initial condition, assuming zero initial condition. Actually, this will be after we learn the numerical method, because some methods which are not specified recently. Anyways, we can see this thing later. Again, prove the derivative of the above solutions is to the response of unit system function. Use the superposition principle to find the solution to the imply. So this also, after we learn superposition principle, means it needs the knowledge of Fourier transformation function. How we can implement the Fourier transformation, then we can understand. Plot the history. So these are questions. Here also, these are the questions. Yeah, we have one best example that related with this, that hydraulic pump pressure force distribution. Area, pressure, force, and the forcing function f of t is equals to pressure times t. So I think this is with a period of 2 pi. So in the next, we can analyze this thing with the period of pi, okay, for various forcing. Okay, this is another type of questions which should be solved. Again, isolation under step load means this related with some sensitive electrical instruments. So this is also another question. Okay. Someone can check these questions and try to solve that. So now, response under general periodic force. That is our topic to be continued. So this is enough for the time being. So thank you very much for watching. Okay.